Hello and welcome to the AI Research Roundup. I am Alex, and today is May 9th, 2025. So today we are looking at a fascinating research paper titled MUSAR, Exploring Multi-Subject Customization from Single-Subject Dataset via Attention Routing. This paper, from Hugging Face's trending list and published just a few days ago on May 5th, introduces MUSAR, a new way for AI to create images with multiple specific subjects, like your dog and cat together, even if it only saw them in separate pictures. It aims to solve attribute entanglement, where AIs mix up features between subjects, using clever attention routing ideas. Alright, so this first figure really sets the stage. We see a collection of images, each one generated by the AI, combining several distinct items or characters. For instance, there is a corgi with a toy car and a lantern, or a cat with a can and sneakers. These examples showcase the system's ability for what is called text-to-image customization, essentially creating specific images from text descriptions, especially with multiple subjects. It highlights how it overcomes, quote, attribute entanglement, keeping features of different subjects separate. This success comes from strategies like debiased diptych learning, which builds multi-subject examples from single ones, and careful attention routing, guiding how the AI focuses on inputs. Building on those initial examples, this next figure shows a core strategy called debiased diptych learning, a method for teaching the AI about multiple subjects using specially prepared image pairs. Alright, so on the left, we see two conditional images, basically single subject inputs, like two different bottles. These are then combined to create the target image, which is a diptych, a two-part picture, showing both bottles in new distinct scenes side by side. The text prompts for each bottle are also combined. This clever pairing helps the AI learn multi-subject generation using only single subject examples. Okay. So while that debiased diptych learning is a great way to create training examples, it can sometimes introduce its own subtle issues or biases. This figure illustrates two key strategies to counteract those. On the left, in part A, we have static attention routing. This is a fixed way of controlling how the AI model pays attention. Essentially, it uses masks, shown as faded areas, to prevent information from one conditional input, like the first image, from incorrectly influencing the information related to the second image or prompt. This helps avoid contamination between subjects. Then, part B on the right shows dual branch LoRA. LoRA, which stands for low rank adaptation, is a technique for efficiently fine-tuning large AI models by adding small, trainable modules. Here, they use two distinct LoRA pathways, one with a higher capacity, specifically for learning the details of the subjects, and another, less complex one, for handling aspects of the overall noisy image. These two strategies work together to ensure the model learns distinct, accurate representations of each subject from the diptychs, without mixing them up. Alright, so while static attention routing and dual-branch low-rank adaptation help clean up the training data, this figure introduces another key technique for preventing mix-ups during image generation itself: dynamic attention routing. It starts with some latent noise, which is like a random canvas for the AI to work on, and the text prompt, for example, a toy and a chest. The system then dynamically figures out which parts of the image, or tokens, should correspond to the toy and which to the chest. This creates a clear one-to-one mapping, ensuring each object gets its information only from the correct source, avoiding that feature entanglement we talked about. So after discussing how dynamic attention routing helps keep subjects distinct, this next figure really brings it all together. It provides a qualitative comparison, a visual side-by-side, of MUSAR against other leading methods. We see several examples, like a toy and a glowing lantern, where MUSAR's generated images are more natural, and the subjects are combined without that attribute entanglement. Importantly, MUSAR achieves this using only single-subject training data, while the other methods often require multi-subject datasets, as noted by the asterisk. This visual evidence strongly supports its advanced multi-subject customization capabilities. Following those visual examples, this table offers quantitative comparisons on the DreamBench test set, evaluating MUSAR against other methods. For multi-subject tasks, it uses metrics like Dino for subject fidelity, so how true the image is to the subject, ClipI for image fidelity to the prompt, and ClipT for text-to-image alignment. Higher scores are better for these. MUSAR notably achieves top scores, shown in bold, for multi-subject Dino and ClipI. This is significant because MUSAR uses only single-subject training data, unlike some asterisk competitors who use multi-subject datasets for their training. Okay, so those quantitative results really underscore the effectiveness of MUSAR. In essence, this work shows it is possible to achieve high-quality, multi-subject image customization even when you only have training data for individual subjects. The key innovations, debias, diptych learning, and dynamic attention routing, effectively tackle data scarcity and prevent that tricky attribute entanglement. It is a really promising step forward for creating complex, customized images. Thanks for tuning in to the AI Research Roundup. Join us next time for more insights.